Alright, hell yeah. So we have dynamics and we set up a problem. You know what I mean? We got a 4-foot ladder, you know what I mean, and maybe a 2-foot step, or however, you know what I mean. So this problem, you have a 4-foot rod, and then we have a 2-foot step, and then we're going to travel this in at 2 feet per second. You know what I mean? This is only 3.5 feet, so within a couple seconds, you know, a second and a half, it's already going to be kind of vertical. And so what we're going to do is, instead of figuring out, you know, how it, like, there's a couple ways you could do this. You could be like, hey, in a tenth of a second, I'm going to be going some sort of, you know, portion of feet. Well, in a tenth of a second, I'm going to be going 0.2 feet. But I think it's just easier to be like, hey, let's move this 1 inch, and then figure out what the time value it is for that. And then we'll use that time value in our calculations. So up here, so here's our origin, and so we make a mark there. When we move the ruler 1 inch that direction, you know what I mean? Then here's the point that we're going to mark, and here's 2 inches. And then I got some other marks just for the heck of it. So we have, if this is 2 inches, this is another 2 inches to 4. If this is a point at 4 inches, here's another point at 8. And so I have grid paper in the direction, let's see, here's the original setup. And so this grid paper is just right in line with the direction of the ruler, because they wanted to know the change in velocity in this direction. And so you can see the first point hardly deviates at all, but the second point moves up 1 millimeter. So hell yeah. So we will have a change in velocity. If this is our velocity component kind of directly in line, this velocity is a little bit changed. It's a little bit up. Also, this is 1.8 millimeters, and we're slowing down even in this second inch. And then if we add these two up, we get like 42, 43.3. Yeah, so that's kind of faster than 42.7. But that's the crazy thing, is even setting up this problem, man, the changes are so slight that it's very difficult to even measure that. But we do have a millimeter change there. So if we have a change in you know, between like the same amount of time, it's going to take the same amount of time in interval to go from here to there as it does to go to here to there. And the time interval to go from here to here is the same from here to here. And so if we're not going as far, you know, distance this way, we're slowing down. So we're going to have an acceleration vector that direction, slowing this ruler down. And 42.7 is, if we doubled this, we should get 85.2, and we don't. We get 83.4. But you can see the change in velocities are very, very tight, very small. So it is actually hard. Like even just that, because that change in velocity is what's going to give us our acceleration, like the magnitude of our acceleration. And because those are very difficult to measure accurately, the velocity vectors are going to be pretty easy to get their magnitude. But acceleration, I don't know, this is just a kind of an interesting experiment to be like, hey, can you get fairly accurate? So that's what we're going to do on paper, and let's do it. Alright, hell yeah. So we have all our points, and what we did is we wrote all our points down. So this is going to be the initial point, B0, and then as we moved 1 inch, 2 inches, 4 inches, and then 8 inches, we mark these. So this is 1, 2, 4, and 8. And then here's our positions, and then this is position 0. So 0, 0 millimeters, and then this is how far we went after. And so what we need to, so what we're going to do ultimately is use these equations. So just generically, the velocity equation is just change in position, change in time. Acceleration is change in velocity, change in time. So what we're going to do, and I guess I haven't figured this out yet, we need to figure out what the change in time was, because we moved 1 inch, we moved an incremental amount of you know, inches. So these 3 points are all the same because we moved an inch between them. this point, and this point, 1, 2, and 4 are the same because we moved 2 inches in between those. And the same thing with these 3 points. We moved 4 inches between those 3 points. All right, hell yeah. So I guess what we need to do is figure out what the time frame on that. And sometimes, man, I just need to use factor label. So we're going to go 2 feet per second. We need to change this. So I'm going to go 1 foot downstairs and then 12 inches upstairs. Hell yeah. So this is going to be 24 inches per second. And I probably could have done that in my head. 2 feet, 24 inches per second. Okay, hell yeah. So what we need is time, you know what I mean? So we need this, you know what I mean? So we need to actually flip this. So we need to say, 1 second is 24 inches. And then how many inches did we go? We went 1 inch. Okay, hell yeah. So that's going to be our time frame. It's going to be 1 divided by 24. So that wasn't too hard. I'm going to store that as alpha t, and then just keep that in mind. So every inch that we go is this alpha t in our calculator, 0.04 seconds. Okay, so now we can start calculating the velocity. So we're going to do the velocity 0 to 1. And it's basically just the difference between these. So we're going to have 21.8 minus 0. But that's going to be the change in position. So we're going to, let's write this out. 21.8 minus 0. And then we need to do the change in time. So we're going to be at this 0.04 seconds minus 0 seconds. Cool. And this is going to be in the I hat direction, and then we need to do the j hat. So we're going to have 0 minus 0, and then that 0.04 minus 0. Obviously, this is just going to be 0, but we have, what is this? And it's not even in millimeter. I don't even, no, this is, holy hell. So we're actually going to have to change our units. I didn't even think about that. We need to change our units to inches. So there's 25.4 millimeters in every 1 inch. And anytime you write an equivalence, if you're new to it, I would write it like this. I don't. But then stack them. And then write both of them, because you never know. I mean, especially if you're kind of new to factor label, you just don't know what you're gonna. But you're gonna. These are both equivalent to 1. You know, I mean, that's kind of what at the end of the day, these are just equivalent. I guess it's equivalent. And then we're going to cancel units. So this has units of millimeters, but I want it to be inches. So we would stack this one right next to it, cancel out the millimeters. See how we'd have 21.8 millimeters. And then we would have 1 inch divided by 25.4 millimeters. Millimeters cancel, and hell yeah, we're just going to have a little bit less than an inch. And then the time value is still in seconds. We're still good there. But we're going to have 21.8. I'm going to put this 25.4. I'm going to store that actually as x. So we can just do 21.8 divided by x, and hell yeah. And then we're going to divide this by our alpha t, and booyah. So now we have our speed on this one is 20. We'll just do 3 decimals. 20.6 inches per second. In the I direction. I shouldn't have done units yet, but we have I hat plus 0 inches per second j hat. Anyway, so that's going to be the first one. All right, booyah. Let's do the next one. Alright, yeah, it's good to go, just kind of overall the pitfalls, not having things ready. But anyway, we'll do better on this next one. So now we're going to have the velocity 1 to 2 in between those two. Yep, just in between those two. And let's spell it out. This is going to be the change in position, change in time. I guess we're going to have that in the I hat, and the change in position in the Y, change in time in the J hat. Okay, hell yeah. Can we just do this one? Well, let's write it out. Again, 43.3 minus 21.8. We do have to divide that by our conversion factor. So I've just said this is x. And then our change in time is going to be the same. Now, this time right here is going to be 2t. You know what I mean? So you could say, hey, the change in time is 0.08 minus 0.04. And then you're still just going to have this alpha t. So essentially, you're just going to have So let's do it. 43.3 minus 21.8 divided by x. That's going to be in inches divided by alpha t. Cool. So we're going to have, yeah, and then I guess I'm just going to store that as alpha a right now because this is the I hat, and then we do have the j hat. We're going to have 1 millimeter. So we're going to have 1 minus 0 divided by that x divided by that t. Okay, hell yeah. So we have x divided by alpha. No. We have 1 divided by x divided by alpha t. Sweet. So we're going to have that in the j hat. So this is going to be alpha. So this is going to be 20.3 I hat plus 0.94, I'm just going to do that, 0.94 j hat inches per second. So there's our second one. And that's really all we need to do this problem now, because now we can do acceleration. What we should do is just average the velocities, because we know, we should know from a fact that the velocity component isn't just 100% in this direction. Like, maybe it is, but I don't think so. Like, I think maybe it is. Maybe I'm totally wrong about that, and it is. You know what I mean? Because graphically, we had no change over the course of a small amount. You know what I mean? These two dots were literally just on the same, or these two dots, from the origin right there to there was no change. So I'm going to keep that in mind, but for whatever reason, it's just like, well, there's got to be some change, right? But maybe there's not. Maybe the velocity component is just all in this direction. This is a cool problem because it's not in the back of the book. So hell yeah. That's why we're doing it just 3 different ways, so we get to learn from it and not freak out that we don't get the exact answer. Anyway, all right, so you could average these velocities, but this one's going to be closer. Hopefully this will just be a better number. And it could, the actual velocity might be just a touch higher. But I think we're in the ballpark on this. Now the acceleration's another animal. Like I said, the only difference between these is 0.3 inches. You know what I mean? So it's not very much. And I should be saving these values. So that's alpha A. And how about 20.6? Should we store that? I'm going to store that as alpha B. Okay, and then this 0.94, I'm going to store that as alpha C. Okay, hell yeah. So the same thing, we just need to change in velocity, change in time. So let's write it out. Now we got to go for the second one because you always take the second position minus like the original position. So we have 20.3 minus 20.6. Now the change in time is still just that alpha t of 0.04 that we've calculated. And this is going to be in the I hat. This one is going to be 0.94 minus 0, and then that alpha t. J hat. Okay, hell yeah. And alpha A, alpha B. So we're going to have alpha A minus alpha B. Yeah, and this is what we talked about in the last video. Is like, hey, or just even when we pick these points, is slowing down. We went farther in the same amount of time, and then we went less far. So we have an acceleration in this direction. That's going to be the negative, what we're calling negative I hat. And don't get too crazy about I hat and J hat. I should explain this every time. It's just the X and Y coordinates, you know what I mean? And then Z's coming out of the board, which would be the K hat. You know what I mean? And then it's the right-hand rule. Wherever the z-axis is, don't mix up your z-axis. You could, but it's just not convenient because you put your fingers in X, roll into Y, and then, hell yeah, the K is coming out of the board. This is going into the board. So this would be the negative K hat. Cool. All right, or the negative Z direction. All right, hell yeah. So I think we're almost there. So we took the difference. We did not take the difference. There we go. So we get a negative divided by alpha t. That time frame's still the same. And we get an acceleration of negative 6.8. This is going to be inches per second squared in the I hat. And then plus, this is 0.09. But alpha, what is that? Yeah, alpha c. So we have alpha c divided by alpha t, and then we're going to get, whoa, yeah, this is actually a lot of acceleration because of the curve up. Hell yeah. So we're going to get 22.7 inches per second squared in that j hat. All right, hell yeah. So we did it. You know what I mean? We kind of got our two values. We got an equation for our velocity. We got an equation for our acceleration. And we can do this a couple more times because we can just do it just with our calculator. So we are going to compare 0 and 2 to 2 and 4. So this one's going to be 43.3. That's going to be the difference in millimeters. Divided by x divided by alpha, and this is going to be alpha 2t. So I'm actually going to go alpha t times 2 and then store that as alpha t now. Okay, so we got 43.3 divided by x divided by alpha t. Okay, hell yeah. So now we got 20.45. You know what I mean? For, you know what I mean? So I'm just going to write these in. 20.45. This is going to be our you know, if we chose to do the difference between here, obviously we're going to get a little bit less, and it's going to be a wrong answer. The smaller you make this change from the initial point is going to be more accurate of the velocity right at that point. Okay. And then the difference here, we are going to have a difference. We're going to have 1 divided by x divided by alpha t, and we're going to have 0.47. Cool. Alright, sweet. So we got the velocity there. Let's get our second velocity component. So we're going to have 86 minus 43.3 divided by x divided by that alpha 2t. You know, keep that in mind. And we get 20 point, I'm just going to, well, I'll go 20.17. I'm fine with that. And, yep. And we got 4 minus 1. So 3 divided by x divided by that alpha 2t, and we'll get 1.42. Okay, hell yeah. So now we do have a change. So we're gonna have 20.17, but we can actually get these pretty accurate. So we can get this one minus 20.45. Okay, divided by x divided by alpha t. Hell yeah! So we get an acceleration. I don't know why these aren't coming out, but that's kind of a bummer. Oh, did I do something wrong? I don't think so. I think I just messed up. No, this is bumming me out. No, and it shouldn't be. Alright, hell yeah. No, I'm glad I'm doing this twice because I made a mistake, and there's no reason to get too accurate. You know, that's the crazy thing about getting too accurate. You're just going to make mistakes. So let's redo this one. I think what got us oh, never mind. Holy Toledo. No, my bad. Because we were converting millimeters to inches, I should have just converted these all to inches just right off the bat. But once we got our velocity equation, now we're already in inches per second. And so, no, it was my bad on me. And we can still get more accurate. So we're going to have the difference between these two. We're going to get a negative number, but I don't have to divide by x. I don't have to convert anything. It's still, this is just the inches per second, and then we're going to divide by that alpha t. Hell yeah. So we're going to get an acceleration of negative 3.4. So this acceleration is going to be reduced because we're going to have the most acceleration right off, because we have the highest speed right there, and then kind of the speeds, like, because this thing actually travels like this until it goes totally vertical, and so you're going to go real fast, but then you're going to slow down, and at some point you're not going to be slowing down anymore. Well, I don't know how that works, but yeah, you're going to slow down the most right here, and then you're going to slow down the least amount, like kind of right in here maybe. Okay, yeah, so that's why we're getting a lower value, hopefully. You know, hopefully our data is accurate. Okay, let's do the next one. So we're going to have 1.42 minus 0.47 divided by alpha t. and this one's going to be 11.4. Yeah, I don't know. You know what I mean? But these, I'm kind of bummed that even setting this up to full scale, it seems like you can't get, you know, like that's where you really have to do a tight window. Like just move it an inch, and we did that. You know what I mean? We moved this very little and found the changes. But these changes are very difficult to measure. But the second you get out here, you know, you might be, you're probably not measuring the acceleration back at this point. You're measuring the acceleration, you know, like if you're in between these 2 points, you're more measuring the acceleration rate right here. And that acceleration might change like drastically, you know what I mean? And then the other point was way out here. So you're not measuring the acceleration right there. You're kind of measuring the acceleration in this zone right there. So that's the only bummer about this. Okay, let's do the last one and see what kind of data we get. Alright, booyah. So the difference here, 169.5 minus 86 divided by x. We got to go alpha t and then multiply by 2 again, store that as alpha t. Okay, 169.5 minus 86 divided by x divided by alpha t. Hell yeah. I'm going to store these. I'm going to store that as alpha a. And now this one, 11.5 minus 4 divided by alpha... whoa. We got to do divided by x divided by alpha t, store as alpha b. Okay, hell yeah. So, that was the difference between here, but we do have to, yeah, I'm going to go alpha a, stored as alpha d, alpha b, stored as alpha e. Okay, we need the original points. That's going to be 43.3 divided by x divided by alpha t, stored as alpha a. This one's going to be 1 divided by x divided by alpha t, stored as alpha b. Okay, so now we have our two velocity components. We have our original alpha a and b, alpha d and e. So we're going to have 10.2 I plus 0.24 j, and we're going to have 19.7 I plus 1.7 j. And damn it, I feel like why isn't... Oh, damn it. So yeah, these are wrong. Holy Toledo. It's between this point and the origin. So my bad. 86, I should have caught that, divided by x, divided by alpha t, store that as alpha a. So this is 20.3. But it's just cool. This is the only way you're going to get, like, check mistakes when you're just like, oh, yeah, no duh. This number's got to be bigger than that number because that's what we're witnessing. And then 4 divided by x divided by alpha t, stored as alpha b. And so we got that 0.944. Now this one does increase, so we are having an acceleration upward. That's definitely what we see. We have a change in velocity in this direction. Alright, holy Toledo. So we're going to have alpha d minus alpha a divided by alpha t, stored as alpha I. Alpha e minus alpha b divided by alpha t, stored as alpha j. So here's my first vector in these two letters. Here's my second vector. And if I do the difference and then divide by t to get the new vector, I'm going to store it just in the lower one. So here's the x value, here's the y value. Alpha I, alpha j. So we're going to have negative 3.5 and then a 4.96 over here. So yeah, we are getting, it seems like less accurate. So let's do this one more time. We're going to have 11.5 minus No, let's do it one more time. 11.5 minus 4 divided by x divided by alpha t. And so this is going to be our alpha E1. And then we're going to have 4 divided by x divided by alpha t. This should be alpha b, and it is. So alpha E minus alpha b divided by alpha t. That's 4.96. Yeah, it's just kind of interesting how No, and that makes sense. Like, we're going to have the most upward acceleration. Well, I don't know. Yeah, are we? You know, that's kind of fascinating. I guess let's look at this, because this value was at an interval of 8, and it seems like we get more upward acceleration. All right, hell yeah! No, this is cool. I'm misunderstanding the fundamentals of how acceleration is because it's squared, because the time value is squared. We have 1 millimeter difference here, and because it looks like we just have 4 times, but we don't. This is going to be a change in 1, and so you're going to need a 4x change. A 4x change would be a change, this would have to be 5, you know what I mean, because here's a change in 1. You already have to include that change in 1, so we only have a change in 3. Same thing here. If this is a change in 4, then you need a 4x change. And so if we came over here, I think that's kind of how it works, where you would have to have 4 plus 16, you know what I mean, a 4x change, not just, don't quote me on that, but that's where you can't just say, oh, that's where I thought the acceleration was accelerating, but no, it was decreasing. So that's kind of hard to read. But anyway, yeah, so this was just kind of fascinating. I don't know what the actual answer is. Alright, this was cool because in this drawing I actually moved it like a whole foot. And yeah, and then I moved it 2 feet. And then we kind of measured the velocity. But we got only 0.8 feet, which is 9.6 inches. You know, and this one might have been a little bit too high. So our velocity equation was 9.6 inches per second, but that's going to be slower. So this thing does really slow down, and if you're taking those positions too far away, then you're like all your speed's in here, and then you're slowing down kind of like exponentially. And so if you take that average speed, well, that average speed is not going to be representative. And so that was kind of interesting that even in our guess, we were half. So yeah, so it's just kind of fascinating, you know what I mean? I'm not super excited about, you know, doing these. I mean, I don't know, it'd be fascinating what the actual answer is, but I have a hard time, you know, even with these having discrepancies. But it is what it is. You know, the farther you take points away from the actual point that you want your velocity and acceleration, the worse the numbers are going to get. So now the part 3 is going to be actually use equations, not like they do in the book, but kind of by brute force, just really changing this just with a change in time of almost a thousandth of a second, maybe even 10,000th of a second, and then measuring those changes. And then you will be able to find the change in position divided by like a thousandth of a second. That's going to give you the velocity. Find 2 velocities, and you'll be able to find, and when I do it with equations, I can back this up. Like with my stick and ruler, I only had a 48-inch, I only had a 4-foot ruler, so I couldn't go the other direction, because you really want to go the other direction to find the velocity coming in, the velocity going out, and then those 2 angles for sure to get the acceleration. Alright, so that's going to be part 3. But thanks for joining me on this, and that's a video.